as much as 10% per annum. It's absolutely essential in trying to deliver gigabit per second throughputs for the highest end 5G devices. It's essential and critical that we enable radical enhancements in energy efficiency per processed bit on the die, both in the baseband and in the RF. Now, our trend over the last 3 generations from 45 nanometer down through 14 nanometer has been to see about a 1.6 times improvement in energy efficiency by generation. And so if you extrapolate, say, between 2015 and 2025, where the really key and large deployments of 5G might be expected for some of the technologies, we can expect to see 6 to 8, maybe as much as 10 times improvement in energy efficiency on the substrate when in active mode. And this leaves aside leakage currents and other critical determinants of idle mode performance. But we see real evidence that the energy efficiency trend will continue. And therefore, we can support, from an energy density perspective, the necessary processing for 5G systems. Then the question becomes, can we pay for those 5G systems, both on the network side and on the device side? Now, this slide shows you, as you would expect, that for advanced process nodes for 14 nanometer and ever more so with 10 nanometer and 7 nanometer, the cost of a wafer is growing, and it's growing in some cases somewhat exponentially. The graph on the left-hand side is the dollar cost per millimeter squared as we've gone through each of those process nodes. And the center graph, though, is the factor that's saving us in economic terms. It is the size occupied per transistor. Multiplied together, you get the dollar cost per transistor, which is the graph on the right-hand side, and we see it continuing to move monolithically downwards. Roughly the same 1.6 to 2 times improvement per generation. So what this means is, and the good news is, that as well as having solutions for 5G systems that do not exceed our battery capacity, we can also afford to buy them, which is encouraging. So number 4 of the 5 elements I described was channel modeling. I think there has been some excellent work in the last few years on channel modeling, especially for centimeter wave and millimeter wave systems. Much of it has been described at this conference, so I don't intend to spend any more time on it. There are important work happening right now in 3GPP and other areas that are codifying the research that has been done in the last 5 to 10 years. I'm confident that we'll have the channel models we need. Then we come to the rather more interesting issue of spectrum. Now, spectrum, for those of you who follow spectrum policy closely, you'll know that the ITU's WRC-15 process closed last week, and there was some quite interesting results coming out of that process. 2 trends at least seem to emerge to me from my uneducated and informal review of the outcomes of the meeting. First of all, we seem to make some real progress on making available centimeter wave and millimeter wave spectrum. Some very encouraging process. And this has been complemented by local regulators taking action on a local jurisdiction basis. In the case, the most notable case, I think the most laudable case has been the FCC in North America, whose recently announced NPRM has made available the projection of spectrum at 28 gigahertz, between 37 and 40 gigahertz, and the possibility of more unlicensed spectrum to complement the WiGig deployment I mentioned a few minutes ago, between 64 and 71 gigahertz. So we have, therefore, a total of about a gigahertz at 28, 3 gigahertz at 39, the possibility of an additional 7 gigahertz at 60. We have over 10 gigahertz of spectrum actively being promoted by the FCC today. And we expect and we appreciate what the FCC has done there, and we expect them to continue that trend over the next 2 or 3 years. And we expect the US to have a leading role in releasing millimeter wave and centimeter wave spectrum for 5G systems. is enormously encouraging in creating a global ecosystem of activity on 5G. The story below 6 gigahertz is a little more mixed. We had some real progress in releasing L-band spectrum, which for those of you who do not brush your teeth every night memorizing spectrum designations, is the spectrum round about 1400 to 1500 megahertz. There was some genuine progress there, albeit mainly as a supplemental downlink technology for LTE. There was some progress at 700. There was genuine progress between 3.4 and 3.8 gigahertz. But there was no notable ITU-sponsored, IMT-regulated progress that I could see personally between 3.6 and 4 and in the 4 gigahertz band. So when we're looking for real opportunities to deploy the 5G new RAD below 6 gigahertz, which is an extremely important area, it may be necessary for individual countries or individual regulators to take action, potentially out with the IMT rubric. And again, I stress this is only my personal view and not those of Intel Corporation, but it's extremely important that we make available new spectrum below 6 gigahertz to complement the millimeter wave innovations to drive the industry. So this is a very important area that we'll have to look at more closely. Now, for those of you who follow standards processes, and some of you I expect attend standards meetings, the question becomes, are the standards guys doing their homework, and do they have a timeline for us that will help us realize LTE-A Pro, the 3GPP 5G new RAT, .11ax, and .11ay in a timely fashion? Now, I've represented some of these on the screen. Those of you who've stayed up till midnight at standards meetings know there's a lot of extremely hard work built into this schedule. But again, I see absolutely no reason why the 4 specifications that I described cannot be realized by 2020. And when I say realized by 2020, I mean in some cases delivered for IMT 2020 accreditation, in other cases perhaps not, but all fully specified, fully actionable. And in many cases, we'll see apparatus before 2020. The IEEE 802.11 PlugFest process has always delivered early solutions. And there are many, many trial systems operational today as Wayne described in the presentation before me. So there is every evidence that the specification setting process and the standards process can deliver what we need. Now, are there devices coming together that can realize these systems? And again, the answer is yes. The previous presentation brought that home. At Intel, we've been doing deep experimentation with FPGA systems for 5G realization, for millimeter wave and centimeter wave IC realization, so that we understand energy efficiencies, die size, area efficiencies, computational complexity, and the key enablers to enable all of the 5G era specs that I described before. And I'm encouraged by the progress that Intel is making and that other companies are reporting too. So to conclude then, in my pragmatic tour of 5G era technologies, I started by asking the question, do we have a clear way forward to generate the growth we want to generate as an industry, to enable us all to fly to conferences, and for all of us to build the kind of future we want for the industry and for the planet, looking to 2030 and beyond? And I think the answer is extremely positive. We have technical specifications coming together. We have a diverse set of 5G era technical specifications beginning to be assembled. We have, based on silicon trends, both in baseband and in RF, the real possibility of realizing those systems. We have an excellent understanding of channel models. We have the beginnings of a very powerful release of spectrum to drive 5G economics, especially in centimeter wave and millimeter wave, and some more work to be done below 6 gigahertz. And we have a clearly defined, actionable timeline for realizing the associated standardization process. So I'm very encouraged. I'm very encouraged that in the 5G era, we'll see a broad and competitive set of specifications that can deliver the kind of value that Intel and everybody else wants to bring to the industry.